Okay, it's 12 o'clock, so we're going to go ahead and get started. I did post your test grades, so those are ready to be returned. I can't stick around after class today because I got to run to the education building for another class. I'll be in my office all afternoon if you want to come get it. Or I'll bring them to class on Wednesday, or I'll just come by your labs this week, so sort of whatever. Super easy. Or if you're in your lab and you want to pop into my office and get it kind of anytime, that's fine. And if my office door is open, of course, you can come in. So, about the test, like I don't know if you noticed your grades or not. I think this one, the grade wasn't quite as high as the first test, so it wasn't done super. So I thought maybe I would offer a couple of tips for trying to prepare for the test. I am going to try and restrict it to just covering sort of the 3 lectures approaching the test. So it'll always be the Monday before, the Friday before that, and the Wednesday before that. So I'm going to try really hard to stay with those 3 lectures every time. You might find it useful as you're getting ready for the test is when there's an example or a problem or anything, or a derivation, anything like that done in class, look at the question, close up your notes, see if you can do it without looking, and then you can go back and peek at the example as needed. So test 2, the one you did last Friday, the first part was basically show Gauss's law with spherical symmetry. That was done in the lectures. The second part was use your result, which was KQ over R squared. Use that to find the electric field inside of an insulator, and that part was done in the lectures. So the first 2 bits, about 2/3 of the grade, was kind of straight from the lectures. Then the third bit was a little bit of a twist. There was a conducting shell on the outside, so you had to kind of think a little bit outside the box if you wanted to get full points on that test. But the first kind of solid 2/3 were straight from the notes. So if you were able to go through the notes and practice them without looking, you're probably really going to set yourself up for success on the test. If as you're doing your studying or reviewing your notes, you have any questions, please reach out. I'm happy to answer whatever I can. In the lab period, if there's a little lull, the lab instructor's there, they can answer all those questions. We're still more or less kind of in material that you can probably also drop into the Help Center for. So if you had questions about electric field integrals or Gauss's law, you're okay to go into the Help Center and ask those there. It won't be till we get into some kind of wonky stuff that I'd probably advise you to stay away from the Help Center. Any questions? No? Okay, well, you know where to find me if you do have questions. So last day we kind of worked on this a little bit, finding electric potential from electric fields. So we're going to do more of that today, and we're going to start off by talking about equipotential lines, which is a way to visualize electric potential. And I did post one new example for today's class. I thought maybe we just needed an intermediate one before we got harder. Probably people didn't have time to print it, but it's not a very long example. It'll be easy enough to write out in your notes. So equipotential lines, they're just a way to look at the potential and get an idea of what that looks like around space. And they're exactly what they sound like. An equipotential line is a line that shows equal potential. So a line that has exactly the same potential. Geography lovers might recognize this sort of map. So this is Mount Fuji, and each of these red lines is a line of constant height. So everywhere along this red line, you're at a height of 2,000 meters above sea level, 2,250, 2,500, and so on. You can do a top-down view, and you see the lines look like this. These equipotential lines in geography give you an idea of how steep a hill is. So like if we focus in on these 2 spots right here, between these 2 points, you go from 2,500 meters to 2,750 over a very short horizontal distance, right? That means it's really steep. You go from here to here over this distance, but just a little ways over, you go from 2,500 to 2,750 over a long horizontal distance. That's flatter. So if you were trying to climb up Mount Fuji, you might choose to go up this path rather than this path because it's not so steep. Equipotential lines are sort of the same deal. When they're close together, that's when it's steep in change in potential. That's where we have a big electric field. So electric field tells us how potential changes. So we're going to draw these lines, and it's going to give us information about the electric field. So I'm going to open up a simulation on FET, and it's going to draw a picture like this. That's what we'll work on. And it will more or less answer the pre-class question from today. I was answering questions, so I didn't remember to open this up beforehand, sorry. Shouldn't take very long to get up. So we've used this before, it's a FET simulation. I'll turn on the grid just so we can see where stuff is. When I put a positive charge in, all of these lines show the electric field. The electric fields point radially outwards. That's kind of something we're familiar with. So this is a 2D picture, and 3D, of course, is coming out in all directions. We can draw equipotential lines, and I can use my little potential sensor to draw that. So if I draw a line, let's say I'll start in at about 30 volts. So I'll put my sensor on top of where it's about 30 volts, and I'll draw a line. If we think about what this line represents, everywhere on this green line, the potential is 30 volts. So if we remember, V is KQ over R, we could solve that equation for R. R is going to be KQ over V. Since V is always 30 volts, R is going to be a constant value. If R is a constant distance from a point charge, the result you get is a circle or a sphere in 3 dimensions. So if we have a point charge or a sphere of charge, our equipotential line or surface will be a circle or a sphere. Okay, so that one was at 30. The next line I'll draw will be 25. Not perfect, but it's okay. So everywhere on this line, the potential is 25 volts. My next one will be 20 volts. So there's another thing about equipotential lines. They're always the same distance apart in potential. So these I'm drawing all spaced by 5 volts. You know, you could do 10 volts, 100 volts, whatever, but it's always the same amount. So there's my 20. Next I'll do 15. And 10 and 5. Okay, so that shows the equipotential lines around a point charge. Some other things we'll notice, and we're going to back this up with the equations. The electric field lines point straight out. The equipotential lines are circles. The equipotential lines are always perpendicular to the electric field lines. Okay, so that's something you'll have to remember. We know electric field is really big when we're in close to the charge. We see that the equipotential lines are close together. So the field is big where equipotential lines are close together. Out here the field is weaker and the lines are further apart. So electric field is small where the equipotential lines are far apart. You know, the electric field tells us about the steepness of the potential. Okay, then another way you might say it is that the strength of the field is proportional to the density of the equipotential lines. Okay, any questions about those things there? No, okay. So let's switch back to our notes. So the equipotential lines are always perpendicular to the electric field lines. That's something we can see if we think about our equation. So the change in potential, so how it changes, is negative of the integral of E dot ds. S would be our path. So that's a little bit of our path. So that's the path along which we're moving. So if the electric field is parallel to the path, I'll just use some math shorthand here. So if the electric field is parallel to the path, then our scalar product, E dot ds, is equal to E times ds times cosine of 0, which is E times ds. So if they're parallel, this whole bit is not 0. So delta V is not 0. So if your electric field is parallel to your path, it means potential changes. Okay, so that's not an equipotential if the potential is changing. So not equipotential. If your electric field is perpendicular to your path, then E dot ds is E times ds times cosine 90, which is 0, which means delta V is equal to 0, which means V is constant. And if V is constant, that's an equipotential. Okay, so that shows us why the electric field lines and the equipotential lines have to be perpendicular. The only way for your potential to be constant is for you to move perpendicularly to the electric field. What else? Our electric field lines point towards low potential. That's something we've covered before. And that comes from this negative sign right here. So delta V gets smaller as we move with the electric field. The next little bit would be these equations right here. So we see that our component of electric field is the change in potential divided by the change in distance. If we have a big change in potential divided by a small distance, that would give us a big electric field. If we have a small change in potential divided by a big distance, that would give us a small electric field. So that relates the electric field lines, or the strength of the field, to the density of the lines. The size of the electric field is proportional to the density of the lines. Okay, questions? So that's some of the theory about it. Let's start with the new example that I posted for today. So for this example, I put in two charges, plus 3q and minus 6q. And our two tasks we're going to do are draw the electric field lines and the equipotential lines for the two charges shown. It's a little while since we did electric field lines, so I did a recap of what we know about electric field lines down here on the bottom. We know they have to point out of a positive into a negative. The number of field lines is proportional to the size of the charge. So this one is plus 3q, this one is minus 6. The magnitude of this charge is twice as big as the magnitude of this one. That means this one has to have twice as many electric field lines. Electric field lines and equipotential lines are perpendicular, and those lines never cross. So electric field lines don't cross, equipotential lines don't cross. So there's some information we know. To draw our electric field lines, sometimes you might want to get a little help from those simulations. If you want to do that, that's no problem. So you could put in a charge of plus 3q. So I'll put 3 pluses right on top of each other. And you could put in a charge of minus 6q if I just put 6 of them on top of each other. One thing this simulation is not the best at is showing the number of lines. It's a fixed number of arrows on the screen. It shows the strength by how bright the arrows are. So over here they're kind of dim, and all the way over here they're still pretty bright. Okay, but that's showing us the shape of the electric field lines. So we can go back and draw those. So we're going to come out of this charge, out of the positive, into the negative. Now we have to remember that because this charge is twice as big, it needs twice as many lines. I have one here, so I need a second one here. I'll draw another line that goes in here. Okay, so this is how we get started. Then we'll draw another one. We'll come out of 3q, and we'll go into negative 6. Okay, I've got one here, one went in. I've got to get another one going in. That one will come from far away. So something like that. I'm not the best artist in the world, but it looks a little bit like this. Any questions? And this is a bit of a recap from Physics 1051, but I thought it might be valuable here. Okay, so that's our draw our electric field lines done. Next, we want to draw the equipotential lines. So to draw those, you can't just go straight from your picture. You need to remember that they're perpendicular to the electric field lines. So if we look at those, we kind of get the idea that we're going to get circles, and out here they might get a little funny shape. You're always welcome to use that simulation if you wish. So we can draw a few of those. So let's get a line at, I don't know, minus 75. Minus 50. Minus 25. Let's see if we can get a 0 in there somewhere. 0 plus 25. 15 plus 75. Okay, so that's kind of what it looks like, and you can use these simulations to help. This charge is smaller, so that 75 volt line has got to be closer, right? So it's a smaller Q, we need less distance to have the same potential, so these are a little bit more spread out. So we can try and draw those on our picture if we wish. I will always be forgiving if you don't get it exactly right. I just expect you to, try as best you can. So I'll draw my lines, and I'm trying to get it perpendicular right here where the lines meet. So this one is going to be 75 volts. This 75 volts needs to be out a bit further. So this one is minus 75. And 50 was about here. 25 about here. 0 about here. So these are the equipotential lines. Okay, any questions about that? So at a, yeah?
Can they cross?
So these blue lines can never cross, and the green lines themselves can never cross, but the blue and the green can cross, and they kind of have to because they're perpendicular. Yeah, good question. So if you're wondering about what would a test level question kind of be, there would be two choices. If there was a simple system of charges, right, so 2-point charges close to each other, I might ask you to draw those electric field lines and those equipotential lines that would look something like this. And I would be looking to know that you knew they didn't cross out of a positive into a negative, that the potential lines had to be perpendicular to the field lines, and those are the things I'd be looking for there. Again, artistic merit, not so much. You definitely do not have to be better than I am at these drawings. The other possibility I might do is I could give you a complicated system of charges, and I could either draw you the electric field lines, or I could draw you the equipotential lines, and then you would have to draw the other lines from those. And I'll try and get some of those posted for homework if you want to see what that would look like. So, what else? I might, based on those drawings, expect you to know the relative size of the charges and the signs of the charges. So let's say, for example, in this problem, I just gave you the blue lines. I would expect you to know that this is a positive charge and this is negative, because it comes out of this one and into this one. I would expect you to know, by counting the number of lines, that this one was twice as big as this one. So I would expect you to know that from electric field lines. Just don't hold your phone. You're not allowed to take pictures of this stuff. I'll post it all, so you'll be able to see everything. Likewise, from the equipotential lines, I'd expect you to look at the values of the potentials and know if the charge was positive or negative. And I'd expect you to be able to see how big that spacing is to know if the charge was big or small. Okay, so if you had one of those maps, that might be the sort of thing I would ask you to do. Okay, any questions? Okay, so let's keep going then. And I did do a printout of that simulation that I'll post with the notes so that you can put those two things together and compare them I would also never expect you to be as good as the simulation is good. I'm not looking for that level of accuracy. I'm looking to see if you remember kind of the basic ideas. Okay, here's the one that was already posted with your notes. So this one is a little bit more challenging. This would be the upper end of what I would give you on a test, maybe a little bit too much. I don't know, it's a little bit tricky. So we want to do the same thing, draw the electric field lines and the equipotential lines, where these three are on a triangle. So here we have three positive charges. What we know is that the electric field lines have to come out of the positive, they're not allowed to cross, and they all have the same magnitude of charge, so they all have to have the same number of lines. So that's the sort of thing we're going to try and draw. We can go back to that simulation if you wanted to get started there. So I'll turn on the grid. So I can put one here, one here, and one here. So that's kind of an equilateral triangle. So you see that they're coming out from every charge. Here they kind of come up and veer away, veer away, veer away, and looks like it's zero dead center, so nothing right in the middle. So we can try and copy that on our picture. So our electric field lines, I'm going to do the easy ones first. These will point straight out. And then down here, these are probably a little bit harder. They come kind of like this, kind of like this. So they're veering away, they're not crossing, and we can put in a couple more on each one. Okay, this picture is not perfect, but it's not bad. It gives us the idea, and it meets all the things we're looking for, that we're out of the positive. It's got equal number of lines for each charge, and those lines don't ever cross. You can label them with the electric fields. So now about the potentials, the equipotential line. We figure that in close to the charges, we're probably just going to have circles. As we get outside, we know it's going to be perpendicular, but it might be hard to imagine exactly what those are right off the bat. So we can look at that on our simulation too if we wish. So let's come in, draw one at 30 volts. 25, 20, 15, 15. Okay, so they start at 35 in close, and then I just reduce by 5 going out to 10. I can do one more at 5 if I want. Okay, so that's more or less what those equipotential lines are going to look like. So we can try and trace those on our diagram, trying to stay perpendicular to the electric field lines. So that's 35 volts. And then 30. These are the equipotential lines. Oh my goodness, sorry. Okay, so I just traced those off the diagram onto my diagram. Yep.
Does this mean there is no equipotential, like there is no potential in the center?
Oh, that's such a good question. So the electric field at the center is definitely 0. What about the electric potential at the center? So that's a really good question. There are 2 ways you could do it. If you wanted to, you could pick a point at the center. You could measure your distance and do KQ over R and add up the 3 potentials, remembering that they're a scalar. So that would be one way to find the potential at the center. If you wanted the electric field at the center, you would still add up the 3 electric fields, but they would have to be a vector. Okay, so the vector versus scalar business is important. If I put my electric field sensor at the middle, and my values, my electric field does actually go to 0, somewhere in here. I'm kind of not finicky enough to find it. So my electric field is shown right here, 0.17 volts per meter. My electric potential at that same spot, not 0, 18.5 volts. So because the potential is a scalar, it in fact does not sum to 0 in the middle because we're adding up 3 positive numbers. Your electric field, where you have to think about directions, that does go to 0. So just because your field is 0 doesn't mean your potential is 0. That was something we talked about with our spherical conductor as well. Okay, so that was a really great question. I didn't think to mention that. Okay, questions? Other questions? Okay, and I've got pictures of that simulation that I'll post with the notes as well, if you wanted to have that to compare. Okay, next, let's do a little more. Let's do a combination sort of example. So we've got a capacitor. We discussed that a little bit. We used Gauss's law to find the electric field between the plates of the capacitor. We also used our integral result to do that, I think. So let's use the expression we know for electric field to find an expression for the electric potential between the plates. Let's use that information to let us draw the equipotential lines. Kind of right off the bat, you could probably look at these electric field lines and know what the equipotential lines are going to look like. You know, these are parallel going straight across. So our equipotential lines are going to have to be perpendicular to that. They'll come straight down and be parallel. So if you're thinking ahead, you can get an idea of what they look like, but we'll figure it out as we go along as well. So our capacitor, let's say our capacitor plates have charge Q, and the plates have area A. So what we know for our electric field is that it's the charge density sigma divided by epsilon naught, and it points from positive to negative. So that's our red arrows in the picture. Those are our electric field lines. Our sigma, since we wrote that down, we should define it. Sigma is charge divided by area, and it's the surface area charge density. Because sometimes the density is more important to think about or easier to think about than the net charge itself. Okay, so there's our field with our definitions made. Next, let's talk about how we're going to find the electric potential. So our electric potential, delta V, you know, it's negative of the integral of the electric field with respect to the path, ds. So let's think about our path ds. When we're talking about a capacitor, it's typical to put our coordinate system so that our origin is lined up with the negative plate, and our coordinate s goes from the negative towards the positive. Just like picking an x and y axis, with a capacitor we pick an s axis, which goes from negative towards positive. At the negative plate, we say s is equal to 0. At the positive plate, it's the width of the capacitor, S equals D, so from here to here is D. And we're going to try and find an expression for our potential at some generic point, and we'll call that distance S. Just so we don't get all tangled up with S's and integrals and limits and stuff, this ds, our integral here, I'm just going to throw a prime down that ds prime so I don't get mixed up between what I'm integrating with respect to and what my limits are going to be. So S primed is going to be my path. So there's my path I'm going to integrate over. And a little bit of my path is ds prime. Okay, so there's my path from the negative plate to that spot where I'm trying to find it. A little tiny bit along that path is ds prime, and it does have a direction, so it's a vector. Okay. Everything okay with the setup so far? Okay, so let's keep going. So in my integral, I'm going to deal with the scalar product first. Negative the integral of the magnitude of the electric field times the magnitude of the size of that element of the path, ds prime, times the cosine of the angle between them. So my element of path is to the left, my electric field is to the right, the angle between those two things is 180 degrees. So that's minus the integral e ds prime times minus 1. Delta v equals plus the integral of e times ds prime. And this is a little bit like what we did last day when we had that wall of the heart cell and we were doing the integral. Same sort of deal there. Okay. So next, let's put in what we know for our electric field, the magnitude of the field. So we've got the integral, the magnitude of the field is sigma over epsilon naught, ds prime. Let's put in the limits of our integral. Our path starts at s equals 0, or s prime equals 0. And it stops when we reach some general point in the middle, which we decided to call s. Okay, so there's my integral with the limits on it. Because sigma and epsilon naught are constant, they can come out front of the integral. The integral of s primed is an easy one, or the integral of ds primed is easy, it's just s prime. Okay, still good? So now, when we did our conductor last day, we talked about how important it was to have a reference point. We had that spherical charge. We said we take our reference point to be that the potential is 0 at infinity. We still need a reference point with this sort of system too. You always need a reference point because we're always talking about delta V, what's the change in potential. So delta V will mean V final minus V initial. That's going to be equal to sigma over epsilon naught times our distance s, that's our final distance, minus sigma over epsilon naught times our initial distance, which was 0. So you can do a straight up comparison here. Vf, our final potential at this point, is sigma over epsilon naught times s, and our initial potential is sigma over epsilon naught times 0, which is just going to be 0. There's our reference point built in for us. We usually say that the potential is 0 at the negative plate. So there's our reference. So at the negative plate, S equals 0 and V equals 0. So this bit is 0, this bit is 0. And then typically we just drop that F right there and we write the potential between the plates of a capacitor is sigma over epsilon naught times S, where S is your distance measured relative to the negative plate. Okay, the last thing that we might put in that's interesting before we start to draw those equipotential lines would be what's the total potential between the two plates, and the total potential is what you would get if your S was equal to D. So for some reason I made two of these slides. I'll just write that result on the next slide. So the potential across the whole capacitor is V equals sigma D divided by epsilon naught. So if you knew something about the charge and the area and the plate separation, you could find the total potential between the plates. We're going to come back to this result when we talk about capacitors, which should be in our next lecture. We won't get to it today, I don't think. Okay, we're also asked to find the equipotential lines. So let's look at this result. The potential is a constant times our distance from the plate. If we want V to be constant, S has to be constant. So our equipotential lines will happen wherever we're a constant distance from the plate. So if we wanted to draw that, the first line where we're a constant distance from the plate can be at S equals 0. So that's my first equipotential line. Another line can be when we're over at the positive plate at S equals D. Another one we could draw right down through the middle. And another one go in the middle of those and in the middle of those. For these, if our electric field is constant, then our equipotential lines are not only evenly spaced in distance, they're also evenly spaced in potential. So both, because the electric field is constant. So these lines are the equipotential lines. They're perpendicular to the electric field lines and they're equally spaced in potential. And like we guessed, those are parallel to the plates. If we wanted to start thinking about energy a little bit, we remember that potential energy delta U is Q times delta V. So we can think about that a little bit too. Delta U equals Q times delta V. So if you wanted to move along any single one of these equipotential lines, let's say if we had a proton that we wanted to move from here to up here, the change in potential would be 0, so the change in energy would be 0. It doesn't take any energy or any work to move along an equipotential line. And we'll try and do some of those combination problems in the problem set that's coming. Okay, questions? If you like the PhET simulations, then by all means, you can set this up on PhET. I did it and I took a couple of screenshots, which I can post with the notes. It's not really that illuminating, so it's probably not worth our class time to do it. Okay, questions? Okay, so let's get going on another example. Okay, I took this example straight from your textbook. And I sort of picked this one on purpose because it definitely goes with everything we've been doing so far, but it reads a little bit funny, so I wanted to give you some practice reading problems to try and decipher kind of what the question is. So in this question, we have electric potential in a region of space. It depends on x, y, and z, where A is a constant. We don't know what A is. X, Y, and Z, those are all going to be measured in meters. So we kind of get a clue that our units for A is going to have to be volts per meter squared. So that's a clue about our units. We want to find an expression for the electric field or an equation. We know something about the work done. We want to try and use that to figure out our constant A. We want to find the electric field from our equation in A at a specific place. And then we want to think about what do our equipotential lines look like at different places in space. So that's what D and E are all about. Okay, so let's start with A, finding the electric field from the electric potential. So part A, here's where we remember we have to take the derivatives. So the electric field is the change in potential with respect to space. So our x component of electric field is minus the derivative of potential with respect to x. I'm going to assume, and you should correct me if I'm wrong, but I'm going to assume most of you are really comfortable with doing derivatives, especially power law derivatives, and that it's okay to jump to the answer. So if this was on a test and you went from this line to minus 2ax, I would call that correct, right? So the derivative with respect to x means you have to do the derivative of each term. These guys don't depend on x, so those derivatives are 0. So we're just doing the derivative of a times x squared. So we still have our a, our 2 comes down front, our power of x goes down by 1, so that's our 2ax, and then we've got the negative out front that we have to be careful not to drop. If anybody's a little rusty on derivatives and wants to come talk to me about it, and we'll go through a few, no problem at all, but I'm just going to assume it would be really boring for you if I went through them all in class. Okay, likewise with our y components, the derivative with respect to y. So the x part doesn't contribute, the z part doesn't contribute. Minus and a minus is going to give us a plus. We've got the a, 2 times 3 is going to give us a 6, and we're left with a y. So there's our derivative there. The z will do the derivative with respect to z. And that looks just like our derivative with respect to x. Okay, any questions there? Yep.
Do you not leave the rest of the function in? So is it like, it's not a 2ax minus 6 3y, or sorry, just
Okay.
function, or
So
you just
that's a
take
good
the
question.
term?
And let's just kind of look at that on a different sheet of paper, just so we don't fill this one up too much. So let's look at the z bit, for example. Ez is minus di v di z, minus di by di z. Okay, the first thing I'm going to do is multiply my a through each of these terms. Ax squared minus 3ay squared plus az squared. So that's your first step, and I promise I am answering your question. Next, when we do the derivative, we know that if we do the derivative of terms added up, we have to do the derivative of each term and add them up. Okay, so we add them all up. And then here's the bit about the partial derivatives. This is the derivative with respect to z only. This means we say everything that is not z is constant, right? So derivative with respect to z means y and x are constant. So that guy is 0, this guy is 0, minus 2az. Okay. We on the same page now? Okay, super. So this gives us our x and y x, y, and z components of electric field. You're not done until you write it down in the form of a vector. So just to finish off the question properly, you say my electric field is minus 2ax, that's the x component, so it gets an I hat, plus a times 6y, that's the y component, it gets a j hat, minus 2az, that's the z component, gets k hat. Okay, so you always do have to write it in that vector form. It's not good enough to just find the components. If you wanted to jump ahead and do part C right off the bat before you did B, that would be okay. Oh no, we need to find A first. All right, so we do actually have to do B first. So part B says we know what the work done when we move a 1.5 microcoulomb test charge, when we move it from this place to the origin. We want to use that information to find the value of A. So part B, A equals what? So it's telling us more or less in the wording of the question how to find the answer. And the way it's telling us is that it says the work done. Right off the bat, you should write down an expression for your work done. You know that work done is negative the change in potential energy. And the change in potential energy is charge times the change in potential. Right? So this is what's given us the tool. We know the amount of work done is 6 times 10 to the minus 5 joules. Q is the charge we're moving around, 1.5 microcoulombs. And delta V is my potential at these two places subtracted. So that's going to be minus Q times V final minus V initial. So I am keeping an eye on the time. I don't expect we're going to finish this example, but I won't take you over time for today. Let's get our two potentials, then we can put our numbers in and solve the problem. So my V final is when I'm at the origin. So V final is V at X, Y, and Z all equals 0. Equals 0. Okay, so my final potential is not very interesting, it's just 0. My initial potential is my potential when I'm at X equals 0, Y equals 0, and Z equals 0.25 meters. So 0.25 squared is 0.0625, so that's A times 0.0625 meters squared. So we can put these in for our potentials. We know our charge, we know our work. So our work done is 6 times 10 to the minus 5 joules equals negative my charge 1.50 times 10 to the minus 6 coulombs times VF minus V initial. So 0 subtract. Oh, sorry, I made a goof when I wrote down my things. So you've got plus Z squared here. That should be a plus, and that should be a plus. Okay, I switched it to a minus for no specific reason at all. A times 0.0625 meters squared. Then we can solve this equation for A. A turns out to be 640 joules divided by coulombs divided by meters squared. And we remember that a joule per coulomb is just a volt. Volts over meters squared, which is what we anticipated for those units in the first place. Okay, any questions? Okay, and then part C is find the electric field at this place right here. And I think we'll have to leave D and E for next day. So part C, E of 0, 0, 0.250. We use our equation we found in part A. So I've got minus 2, 640 times 0, plus A times 6 times 0, minus 2 times 640 times 0.250. Gives us an electric field of minus 320 volts per meter. Okay, so we'll quit there for today, and then we'll pick that up again on Wednesday. And this is the cutoff for our test now on Friday. Today and our last two classes before today.